uses a pair of analog devices, ADSP 21161N Shark chips. That's the actual digital signal processor chips in the device. There's two of them in there. It's the same chip that everybody and their dog uses industry-wide. You can go to your local big box electronics store and you can buy a surround sound processor which contains one of those chips. You can also go to Studer, buy one of their Vista 8 consoles, which are just the sexiest thing on wheels, and the outboard rack, the actual brain rack for that console, if you buy it fully loaded with every option, has 126 Shark chips in it. Cool. But sheer quantity doesn't really tell the story, because there are different ways to use those chips. And how you use them oftentimes matters more than how many you have. In this particular case, what we're talking about is the Shark chips are named after their programming language, Super Harvard Architecture, Shark. And Shark programming language is kind of like Visual Basic. It's got a lot of pre-built modules you can kind of stick together, which is part of what made them so popular, is you can make processing objects just fast. Slap them together in no time. It's great. Allows you to really kick out a functional product in very little time. Along about the middle of the Shark 2 life cycle, the Analog Devices guys released a new programming language called SIMD, Single Instruction Multiple Data. And SIMD is more like programming in machine-level code. It requires a lot more work on the programmer's part to create processing objects, but you end up with these special SIMD processing objects which are able to run two streams of digital audio through the chip at the same time, truly simultaneously, as long as they're both getting the same mathematical function performed on them, same mathematical operator. They can run simultaneously on the same clock cycle. It's a big deal. Very big deal. If I can get my button to work here. There we go. What that does for us is gives us a little bit more free space on our DSP. What I mean by that is if we take an empty blue 16, that will be sitting at 4.4%. And if we add to that a compressor, a gate, and a gain, we end up at 10.2%. So the compressor, the gate, and the gain cost us 5.8%. All right. So if I add another 5.8%, another channel of compressor, gate, and gain, I should be at 16%. But I'm not. I'm only at 10.6. What's that all about? It's largely about SIMD. It's able to run those digital audio channels through the chip simultaneously, take advantage of SIMD. Now it's not perfect. We're still getting a 0.4% overlap. And there's still some gaps that we could have used, but because of timing or whatever, we weren't able to use them. But it's still a pretty darn good improvement. Now my first two channels there cost me 6.2%. So adding two more channels should put me at 16.8. But it doesn't. It only puts me at 13.8. Again, that's because of SIMD, finding additional efficiencies. More channels puts me only up to 20%. If we look at our breakdowns, first channel was 5.8%. The rest of the channels are incredibly inexpensive. None of them are quite as good as the second channel. The second channel is always your winner. But even our channels 5 through 8, 4 channels cost us 6.2%, a little over 1.5% each. Not bad at all. That's how we save you some processing power in the Shark chip. These same processing objects also work with the new 4 times as fast chip in the 160 and the 800. It's still the same family of chip. It's just a 4 times faster clock rate. It's like buying a 2 gigahertz computer instead of a 500 megahertz computer. All right? Now, something else that goes right along with that is a thing called scalable processing objects and the reiterative object compiler. Outside of this class, I almost never say reiterative object compiler. Instead, we call it the ROCO. And the reason is, you're at a trade show talking to people. If you tell them about the ROCO, you're much less likely to spit on them if you say reiterative object compiler. ROCO is a safe name. Better name to use. Scalable processing objects. I know you all did the training modules, right? Yeah, nod your head and smile. You've all seen the scalable processing objects, but I just want to show you real quick here why they're so important. If we have 5 mic signals being mixed down to 1 output, in the bad old days, we would put them in an 8-channel mixer. That would take roughly 8% of our total DSP power. With scalable processing objects, I can change that to a 5-channel mixer. And instead of taking 8%, it only takes 7.6%. That's huge. It's absolutely huge, whether you realize it or not. All I did was turn off those 3 channels, and I saved 0.4%. Now, why am I getting all excited about 0.4%? It's only 0.4%, right? Not that big of a deal. Yeah, it is. 0.4% is a free compressor gate and gain right there, channel 2. So that little tiny savings, that little bit of savings that you got from turning off those 3 channels, because your processing objects are SIMD objects, you can use that to buy a whole bunch of other stuff. So scalable processing objects all by themselves are kind of cool. SIMD all by itself is kind of cool. You put them together, it's really cool. Very, very cool. Now the final thing is the ROCO. Opening up a new design file here. As soon as it opens, I'll turn on the sharing and let you see it. There we go. And the full screen button's got to be off by now. Yep. Switching sources always does that. There we go. I loaded a new design file, and in the system output, I see application started, file created in build 462, last saved in 587, file recovered never. That's kind of cool. I never crashed this file. Me. And then the 188 lines down there, the important ones. Compiling, algorithm type audio path, compile success, applying best solution, best compile iteration, blah, blah, blah. What the heck does that mean? Well, the ROCO does not compile your design file just one time. It compiles it, then it turns around and tries it again with a different set of settings. And it tries it again with a different set of settings. And tries it again with a different set of settings. It'll compile in the order that you placed the objects first. So it'll go in and compile your objects 1, 2, 3, 4, 5, 6, 7, 8. Okay, cool. Write down the answer. What percent utilization was it? And then it'll compile your objects 5, 6, 7, 8, 1, 2, 3, 4. Okay? Then it'll compile your objects 1, 3, 5, 7, 4, 6, 8. And then it'll compile your objects something else, something else, something else, something else. It goes through all these combinations until it gets to a point where it's obviously just not getting any better. In some cases, it's getting quite a bit worse. But at that point, it knows with a high degree of certainty what's the best way to compile these processing objects to use the least amount of DSP power. Then it goes back and it recompiles them that way. Now, the system output does not tell us how many compilations it did. But it does tell us the best one was number 18. So we know that since the compilation starts at 0 and 18 was the best one, that it had to have done at least 19 compilations. How long did it take to compile this design file? 9 times? Well, compiling started at 43 seconds after and started at exactly, or ended at exactly 00. So 17 seconds to compile that design file. 18 times. And bearing in mind, that's compiling the design file 18 times on this computer while this computer is running the training software, which is a huge CPU suck. Big time. Big time, big time, big time. On my laptop, it will compile the same design file in about 9 seconds. No problem. And that compiling happens in the background. You don't even see it happen. Look right down here. See these 2 red and 2 green icons down here? Those will turn gray and kind of flash around in a circle. Anytime the compiler is running, you also see it listed over here. So if I go up here and I grab the wire, and I disconnect it from the gate, the compiler starts back up again. It starts to recompile. But before it has time to do that, let's go in here and I'll grab an EQ, parametric. Stick a parametric in there. What's going to happen? It's going to abort the compilation and just start over. Give it time to get started again. Just for an example. Then I'll put another wire in there. And it aborts it again. Starts over. And all this happens in real time in the background. You never even notice it's happening. If you have a computer like mine, where the CPU fan is responsive to CPU cycles, you'll hear the fan kick up to high speed when the compiler starts, and then drop back down when it's done compiling. Other than that, you never even notice the darn thing's running. Doesn't slow you down, doesn't lag your screen out. You don't notice any difference. It just runs along in the background, does its thing. And this, just so you know, is a fairly chunky design file. This is processing for 44 output zones in a dome. 44 output zones that all have EQ, gain, delay, and limiter. Each of 44 zones. So it's not a cheesy little easy design file to deal with. Take that EQ back out, it starts compiling again. Fire that up, and abort, start over again. And somewhere between 6 and 18 seconds later, I have my result. The Roku is pretty cool. It's running constantly in the background, constantly looking for the best solution. If you ever see a bunch of PSS engineers hanging out together, look for the little short guy that looks like somebody brought their brother along. Little skinny guy. That's Alex. That's Alex Crowley. He's the one who wrote the Roku. Go give him a handshake and congratulate him on a job well done. And he does look like somebody's little brother. Completely. He just looks like somebody brought their brother along to the party or something. Any questions on the Roku or SIMD or any of that fun stuff? Yeah, the one person in this training who's actually met Alex is laughing his full head off right now. True, it's what he looks like. I mean, he's just kind of this unassuming little guy. He's fun to go to parties with. Tell you that for nothing. Oh my gosh. Better have a ride home. End up wandering around the city with Alex all night. No questions. All right. Where is my list o' happiness? There it is. Oops. Scrolled off the screen. I want to take a little bit of time here just so we don't miss them. Because we tend to run out of time and I don't get to tell you guys about some of the cool stuff. I want to make sure we cover some of the topics that are new toys and new cool stuff in version 2. Things that sometimes get missed. And some of them I'll show you, some of them I'll just tell you about, depending on what the heck they are and what's going on. The first one I want to talk about is the audio coupler. And you guys actually saw the audio coupler earlier in room combined example file I showed you. But I'm just going to take these wires out, slide this over, give you a little real world example what the heck the audio coupler is for. Under Tools, Audio Coupler. It starts off 4-channel, but you can make it up to 32. For this, we just need 8. what the audio coupler does, if I can get it wired up right, there we go. Over here under properties for the audio coupler, we can change the signal name of each thing that goes through it. The audio coupler does not do anything to the actual signal, it just changes the signal name as it goes through. So this might be zone 1, this might be zone 2. The names changing there on the screen as I type these in. So now our outputs are actually named. Wherever this bundle goes, it'll take those names along with it. That's the audio coupler. Cool piece of gear. We had a question. On SIMD, if there's no signal connected, there's no processing involved. Yes and no. There's two issues there. If there's no signal connected, like with this compressor, we'll give it a minute here to compile. You'll see in the compiler report, we've got some errors here because it has no inputs wired and no outputs wired. Watch what that does to the system output. Still compiling. Now it's in yellow instead of green. That's because you've got a warning. This object isn't passing audio. And London Architect considers that to be kind of odd. If I delete that object, give it time to compile here. The longest 14 seconds in the world. It's waiting for the compiler. It's so funny. The Roku is so blazingly stupid fast. Yet when you have to sit here and wait for 12 seconds, it seems like you're going to die. Could be worse. You have to go load your design file into a separate compiler. Stupid as that. Now it's green, but notice it says 83%. So if that compressor is in there, the Roku still tries to estimate how you would use it and how much DSP power will be taken up by using it. So it reserves that DSP power for the compressor, and it reserves it truly in a worst case scenario. It'll reserve the maximum amount of DSP power that compressor could ever possibly use. No SIMD, no anything helping it out. So you should not leave processing objects just laying around your design file. They don't actually use any processing power, but London Architect thinks they will, if that makes sense. In other words, if you were to load this design file, Blue 80 would never actually go past 83%. If I had the compressor in there, I mean. It would never actually go past 83%. But London Architect thinks it's at 85%. So when you get to 100, it'll stop you, even though you're actually just wasting some of that power. That makes sense, I hope. One of those things where the answer is yes and no, all at the same time. By the way, for anybody who cares, down here in the system output, these are all my devices coming online. Right here in the middle, adding node. I turn around and power my rack up while we're talking. Okay, so we looked at the audio coupler, which is really cool. Change signal names, that is so cool. You can drop it down to one channel, have up to 32 channels. You've seen me a couple times today go right-click, properties. That's new in version 2. That didn't exist before. For anybody who's used a wall pot volume control in the past and bumped up against the fact that there's no way to sub-range limit volume of that wall control, well, now there is. Always in the past, like for instance, if I had a, well, here we're using an N input gain, for instance. This N input gain, wow, that was a loud noise. On this fader, I can set a sub-range and say this fader only goes from negative infinity to negative 10 dB. or maybe it only goes to 0 dB. Okay? But that does not change the processing object. That just changes this control. On the processing object itself, there's no subrange limit. So if I were to grab that control and drag it onto a control port or an external pot, the control port is still negative infinity to plus 10. Well, now the gain object, it's the only one that does it, but that's the one you need it to do. The gain object has a subrange right on the processing object. So you can tie it to an external control port, have it subrange limited, so you can say, okay, the customer can turn the volume up to 0. You can't turn it up past that. Or they can turn it down to negative 40. They can't turn it down all the way. One of those features that you really don't care about unless you bumped your head against it in the past, in which case you're sitting at your desk right now going, yes, this is awesome. Here's another one for you. Oh my gosh, oh my gosh. Let's go to operate mode with this big bad boy. Like that little screen glitch I had there? That was pretty cool. In the configuration window. And here's the problem you always have when you're tuning systems. Okay, I'm in operate mode. Pretend I'm online actually working with the system. And I go in here to my parametric. And let's say I bought the worst speakers ever made by any manufacturer. And so here's the curve I ended up with. Okay, there's my perfect tuning for my speakers. Nice. Well, the problem is, or was, if I wanted that same curve, darn it, wrong button. If I wanted that same curve on all of my EQs, maybe the first 8 EQs are all the same speaker. So I'm going to start with the same curve on all of them and then just go tweak it, right? Well, in the past, to copy that curve from one EQ to the next, you had to go out to design mode, right-click, copy, paste. Now, in operate mode, you can right-click, copy parameter values. I'm going to copy them to the buffer, right-click, paste. Right-click, paste. Right-click, paste. Just that quick, I set all 8 of those EQs the same curve. Previously, that would have been a complete pain in the rear. Took forever to do. Again, it's one of those things that if you've never bumped your head against it, you probably don't think it's very impressive, but trust me, it actually saves a lot of time. I'm not going to show, I'll show you later, but just in case I forget to mention it, the Blue 10 wall controller now has a contrast knob on the control panel. Very nice. Had that for a long time. We also now have, this will be interesting, let's go delete this. That's an old N input gain right there. We put in a new N input gain and make it 8 channels. And if we look at the control panel, oh, my bad, it automatically updates them. I didn't realize that. Cool. All right, well, right now here's what I'm talking about. This is no name. On the mixers, the auto mixers, the N input gain, and the I/O cards, it automatically shows on the control panel signal name right at the bottom of the control channel. It's like on your mixer now. It'll tell you what signal is going to every channel of the mixer right there on the panel. Very cool feature. We also have, previously, if you've run up against the just insanity-making problem of once upon a time, the source, let's make sure it gets right, the source selector could do incoming signal names. It had the use signal names property. the source matrix had the source names property. You type in a name. Now they both have both. They used to work in two different ways. Now they both do both. Again, a lot of this stuff, if you haven't bumped up against it, don't care. Next one we'll talk about when it comes time to do security. On the graphic EQ and the parametric EQ, we got a couple of cool new features. Convert that to a custom panel. Did I have to convert it? I think I did. Pretty sure I did. On the graphic EQ, you've got this great curve that shows behind it. It's just awesome. It's a predicted curve. I'm going to make a copy of this down here. And that predictive curve, you can actually turn on all filters too and see the components that make it up. And so it makes a great display on a control panel. But the problem was, in the past, there was no way to make it so you could see that display without making it so you could actually edit them. Now, you can turn off show faders for that control, and all you see is those response curves. On a different page, you have the actual controls. Makes sense, I hope? It's a cool new feature. On the parametric EQ, you guys have dealt with speaker manufacturers' tunings. What's the most annoying thing in the world? You look on the sheet from the speaker manufacturer and it tells you the type of filter. Gives you either the slope or the width. I'm sorry, the slope or the slope or the width. But the problem is, on a lot of manufacturers' sheets, it doesn't tell you the width. It tells you the Q. Instead of width, it says Q. Well, now you can click on that, or you can select all of them, either one, and change units from default Q. Now they read out in Q instead of bandwidth. Doesn't change what it says up here, but it will read out in Q instead of bandwidth, which is really pretty cool. On a default control panel, there's no way to show Q and bandwidth both. You have to choose one or the other. If you wanted to, you could convert this custom and have it to make the whole thing wider, of course. Make room for it. We just copy it over here. Leave these set to bandwidth, Fahrenheit, bandwidth, and change these to be Q. So you have both of them on the same control panel if you wanted to. If you ever done any speaker tuning, that's a big deal. That's a real big deal. Let's see, where are we? Just checking my list here. We did room combining. Sorry about that hideously loud noise. Hopefully it wasn't actually hideously loud. Oh yeah. What we can do next. See if I can get my server to show up here. There he is. The screen's going to go blank for just 1 second while I go to my server and launch some tunes. Not for my personal entertainment, but so we have a signal on our DSP to play with. Not that I'm not going to very carefully pick a good tune. Well, it's a Brian Setzer. Okay. Signal's rolling. Let's go online to this blue 16. What? What did I do? Oh, good grief. I'm running beta software on my computer. You know, somebody ought to just slap me. But updating firmware in one blue 16 is faster than reloading the software on the computer, so we'll do it real quick. By the way, here's your firmware update process for those of you who've never done it before. When you open up your design file, it will say, if your design file's from an old version, it'll say your design file's from an older version, do you want to update the file? And it'll warn you that if you update the file, you can't open it in old versions anymore. A design file you create today will work in today's software and tomorrow's software. It will not work in yesterday's software. Then, when it comes time to go online, you are prompted with that message you saw that says some of your devices need to be updated firmware. Would you like to update the firmware? Hit yes, hit OK, and it does its happy little thing, which is what it's doing right now. It takes about a minute, minute and a half to do it. When that's finished, the little OK button will light up in the bottom right-hand corner. You hit OK, and you're done. Nothing else to it. Very, very simple process. Let's see. While it's doing that, let me tell you about some of the things here. There is a utility in London Architect to convert a Blue 16 device, after it's been programmed, into a Blue 160. There's a device to convert a Blue 80 into a Blue 800. A couple of utilities that are missing, in my opinion. Like, there's no way to convert an 80 to a 160, which I think we should have, but we don't. That's life. But be aware those are there. So if you've got a design that you started working on 6 months ago, and it, of course, only had a 16 in it, or only had a couple Blue 80s in it, and now, further down the road, you want to upgrade those and use new gear, because you haven't done the installation yet, you just done the design, it will convert it for you automatically. If you have a design, you've designed it in like a Blue 80, and you want to use a 160 instead, give me a call, because you don't have to start over from scratch. You don't have to start from scratch at all. There's a way around that, and a way to make your life much, much easier. That's the device conversion. The Blue 8, we should talk about the Blue 8 during class. That's what I was going to do next. So I won't tell you about its changes yet. So all we have left then is dynamic meters, really. And stuff we'll talk about during security and during logic and stuff later in class. The next hour, we're going to talk about logic control, how to program logic. So we'll actually take a break a little bit early here from this hour, because logic can be a fun conversation. Out of all the topics, that's the one we tend to run long on the most, because it's a lot of fun to play with. Firmware process is just about done. Seems like it's taken 8 or 9 years to finish, hasn't it? Probably been, what, a minute and a half? Sit here and squirm. Come on, aren't you done? And you can update firmware in multiple devices all at the same time. Actually, it's kind of fun if you watch the data traffic, like on a switch or with Etherreel or something. The whole 3-minute process of updating firmware, about 2.5 seconds of that is transmitting the firmware to the device. All the rest of it is the device doing its own thing. For most of that 3 minutes, the computer could just drop dead and nobody would care. It takes about 2 seconds to squirt it up there, you're done. Let's go online to this turkey, now that we've finally updated our firmware. Dynamic meters. In the past, we always had meters over here, which you guys will see in just a second. Yep. And we've got our output meters. And if you wanted to check anything in between, like right now, let's say on this design file, I have output at 3 and 4, but no output on 1 and 2. I'm trying to figure out why I can't hear anything. Well, if I hover over a wire, a meter pops up. Hover over this wire, a meter pops up. This one says negative 10 dB. This one says negative infinity, so maybe this input gain has got the problem. Pop it open and unmute it. You can also take those dynamic meters and you can pin them in place. If I click on a little thumbtack there, now when I move off of it, the meter stays there. I go over here, pin one here, I've got 2 meters in real time there. Come down here and hover over it, pin one there. I want to monitor both sides of the stereo image, for instance. Don't do that. That's the one thing you can't control, is the up or down. You can control which direction from the wire it goes. There we go. Sometimes it makes decisions that I don't care for. I'm pretty sure there's some logic to it that be overridden, but I don't know what it is. So that's what dynamic meters are. Dynamic meters, now, they do take up DSP power, even when they're not being used, because the DSP has to reserve DSP power for all those meters. By default, your device will be capable of 2 dynamic meters. Look up here. Right now I'm sitting at 19.3% by DSP usage. And a big part of that is because I've enabled 20 dynamic meters. What the heck do you need 20 dynamic meters for? Let's put it back to 2. Back online, have to reload because I have to load it without the meters turned on. And instead of being at 19.3%, now I'm at 7.9%. So those other 18 meters took almost 12%. Now I have 2 dynamic meters. So there's the first one that pops up. I pop a second one up, pin it in place, hover over a wire somewhere else, nothing happens. I'm only allowed 2 at a time because that's what I have set under properties. So you can save some DSP power by not cranking those up. Again, they'll default to 2. They won't default to 20. Not quite that stupid. And if you're not going to use them, if you're just scrapping for every last little bit of DSP power, you can always turn it off. You see our DSP power has dropped down to 5%. The only thing is, once it's up and running, if I hover over that wire, nothing happens. Now, as long as we're on that topic, let's finish this hour out with DSP utilization. Worst case usage, 4.4%. Actually, let's turn the dynamic meters back on. Here's the default Blue 16, 6.4%. Turn off those dynamic meters. We're down to 4.4%. Where's the rest of our DSP power going? Where's that 4.4% going? What the heck's it being used for? Any guesses? Input cards and output cards all have meters on them. Somebody's got to control those meters. In this case, it's the Shark chip. Turn those meters off, drop down to 1.4%. What's sucking up that last 1.4%? Nobody has a guess? That last 1.4% is the 1.4% you cannot turn off in a Blue 16. It is, again, meters. Those flashy little front panel lights, little meters on the front of the Blue 16, have to be controlled by a DSP chip. They're controlled by the Shark chip. That's 1.4% of its processing power is used up by those front panel meters. No way to turn them off. So that's the best you're ever going to get. Now, if we go to a Blue 80 with the dynamic meters turned off and the input and output card meters turned off, we end up at 12%. The heck is that? Well, 1.4% of it is the front panel meters you can't turn off. The other 10%, It's a router that you can't see. Actually, you kind of can, you just don't realize it. That router is right here. It's routing in and out of CM1 module. That'll always be there. That's the DSP overhead that it costs for the Blue 8 to talk to the CM1. I go to a Blue 160. Turn the meters off. Oops. Meters off. Side. These meters off. I'm at 3%. That 3% is reserved DSP for BlueLink. I set up this BlueLink node to use 16 channels. The 3% jumps to 9%. So there's 1.5%. Actually, it's less than that. It's more like about 0.5%, a little less, 0.4%, which is used for the front panel. And then the rest is reserved for the BlueLink nodes. That's what makes up that initial blob of used up DSP power. 3.1%. You ready for this? This gets even more confusing. The Blue 800. Oops. Got to turn off the dynamic meters. Nope. 15%. What in the heck? Why is the Blue 800 using 15% of its DSP power when the Blue 80 only used, what was it, 12%? Yeah. The 800 is supposed to have 4 times as much DSP power. What's that all about? Well, the worst case usage isn't necessarily all about processing objects. It's also about everything else down here. Cycles, there's our actual DSP cycles. We're actually sitting at about 5% right now, which is on one chip. So you call it 5.4%, but then you divide it between 2 chips to average it out, and the meter should really say 2.7% right now, not 15%. But we're also using up bus ports. What the heck is a bus port? A bus port is each chip, there's 2 chips in the box, each chip has 128 inputs and 128 outputs. Now on a Blue 80, we don't have to reserve any of those inputs or outputs. Because you think about it, a Blue 80 has potentially 32 CobraNet signals and potentially 16 analog signals for a whopping total of 48. So yes, it should have been called the Blue 48, but we won't argue about that right now. So you can't overload the 128 input channels. However, the Blue 800 has CobraNet and BlueLink. Because BlueLink can grow and shrink, you never know how many ports it's going to need. You have to reserve 32 of those ports ahead of time for the CobraNet module. You also have to reserve some of them ahead of time for the analog ports. Otherwise, BlueLink could gobble them all up. That's why that reads 15%. If I start throwing in processing objects, building a design file, it's going to sit right there at 15% and do nothing until I get enough processing objects in there to break over the 15% mark. Then it'll start going up. That's why this little percentage readout on the Blue 800 is kind of weird sometimes, because it's trying to show you a bunch of different things on one little bar graph. It's not necessarily simple to do. Now that also brings up an important issue on the BlueLink. Blue 160, just like in the original series, the Blue 16, because it's not using DSP power to talk to the Cobra Net module, Blue 16 has more DSP power than a Blue 80, really. Because you give up 10% of your power in the Blue 80 just to talk to the CM1. Blue 160 can process more channels of Blue Link audio than a Blue 80. The Blue 80 has 32 channels reserved out of 128. 32 channels reserved for Cobra Net. So you end up with only 96 Blue Link channels. Whereas the Blue 160 can process a full 128. So that's what that little resource meter that doesn't always make sense. That's what that's trying to tell you. Questions on that? All right. Let's take a break. Oh gosh, we're not even all that early actually. I thought we were going to finish that hour up early. It's almost 3 o'clock, so let's just call it 3 o'clock. And we'll take a break until 3:10. And we'll come back and talk about logic.